Okay, we're coming to the end of chapter 7, which is on techniques of integration. In this video, we're going to go through the last section, which is on improper integrals. And so what improper integrals are going to do is they're going to allow us to fill in all of the gaps as far as everything that we aren't able to integrate with a definite integral, that we haven't learned how to integrate with a definite integral up to this point. So if we think about definite integrals from the perspective of areas under curves, then we can't integrate going off to infinity. We can't integrate at an infinite discontinuity. And technically we don't know how to integrate at any discontinuity. At certain discontinuities, we would have a sense of how to do it. So if you had a jump discontinuity like this, I think we could use our intuition. We know that the definite integral represents area under the curve, so we could use our intuition to get this definite integral. But we haven't technically talked about how to approach this officially from a math standpoint. How do we look at this? So that's what improper integrals are going to allow us to do. Once you've learned improper integrals, then you're able to evaluate any indefinite integral across any kind of discontinuity going off to negative infinity, positive infinity, etc. Okay. In defining a definite integral, so the definite integral of the function f of x over a to b, we dealt with a function f defined on a finite interval, and it was closed at the endpoints, right? The function was defined at the endpoints. Otherwise, if the function weren't defined at the endpoints, if you think about it, that kind of would create an issue based on what we've technically learned up to this point. And we assume that the function does not have an infinite discontinuity. In this section, we extend the concept of a definite integral to the case where the interval is infinite, and also the case where the function has an infinite discontinuity in the interval. In either case, the integral is called an improper integral. One of the most important applications of this idea of probability distributions will be studied in section 8.5. So they only mentioned going off to positive or negative infinity, or the case of an infinite discontinuity. That's the main purpose of improper integrals, but we're also going to use improper integrals if we were integrating over the open interval from a to b. Well, we can't, if it's open from a to b, the open interval, we can't say, or let's say it's open at a and closed at b. Okay, but the function is not defined at a. Now, at this point, I think intuitively you could figure this out on your own how to do it when you think about the definite integral from the perspective of areas under curves. But even then, technically from a math standpoint, you can't write this because it's not defined at a. So how do we deal with that? And same idea with a discontinuity within the interval other than an infinite discontinuity. How do we integrate across that? Okay, but we're going to start with what they're calling type 1 improper integrals, and these strictly are dealing with going off to infinity, positive or negative infinity. So we're calculating the area under the curve, but the curve never ends, right? What if we want to say, so it says consider the infinite region S that lies under the curve y is equal to 1 over x squared above the x-axis and to the right of the line x is equal to 1. So this is the curve 1 over x squared. It's always positive as x goes to infinity. And if we're thinking about this region here, this area going from x is equal to 1 all the way to infinity, is that something we can integrate? And so they say here, you might think that since S is infinite in extent, its area must be infinite. Yeah, you would think we're kind of wasting our time. I mean, we could never evaluate an integral like this. It would never exist, right? But it says, let's take a closer look. The area of the part of S that lies to the left of the line, x is equal to t. So they put this line x is equal to t here. Okay, so we can think about the area from 1 to t is this. That makes sense. Right? Now we can integrate that and we get a function of t. Okay, it says, notice that, yeah, the a of t, yeah, this, no matter how big we make t, this is always going to be less than 1 no matter what. So that's interesting, right? It's not like the area is not like ballooning. It's, you would think that an infinite area is going to just always get bigger and bigger and bigger, but this infinite area, no matter how far out you go, like if you integrate from 1 to infinity, that it's never going to be greater than or equal to 1, that area. So when you look at it from that perspective, that's interesting. And then, but what does this remind you of, though? That what we're doing here, we can think about, well, let's take the limit as t goes to infinity and call that the area, right? The limit as t goes to infinity we see as 1. And so we can think about then, you just saw here, we can think about the idea of integrating something going to infinity, and it actually equals something. And so the area of the shaded region approaches 1 as t goes to infinity. So we say that the area of the infinite region S is equal to 1, and it's written like this. The integral from 1 to infinity of 1 over x squared dx, and you view that as you replace the infinity with a t, with a variable, and then you take the limit as that t goes to infinity of this integral. And so all you end up doing to solve these kinds of problems, you just solve this definite integral and you get a function of, in this case, t, and then you take the limit of that function. Okay, so here they're showing when t is equal to 2, you get this area. When t is equal to 3, and, as you make t larger and larger, it approaches 1. Okay, so it says, using this example as a guide, we define the integral of a function, not necessarily a positive function, over an infinite interval as the limit of integrals over finite intervals. Yeah, so there's no restriction here. Like, it doesn't have to be, the function doesn't have to be positive. All you're doing is you're just thinking about it like it says here. You're just going to, the part that you're evaluating to infinity, you replace that with a variable. And you can absolutely think about taking an integral of any function. I mean, as long as, I guess it's for the moment, as long as it's continuous. We don't know what to do with other types of discontinuities yet, but if you think about that, it's continuous, and so you can put t wherever you want, and you can evaluate the finite interval. So you're just thinking about, as you keep pushing t back, what's the limit of that? Okay, so these are improper integrals of type 1. So if this integral from a to t of f of x dx exists for every number t is greater than or equal to a, then the integral from a to infinity of f of x dx is just the limit as t approaches infinity of a to t f of x dx, provided the limit exists. So it might not exist. It might diverge, right? Depends on, it might be where the area doesn't converge to anything, depending on the function. Okay, but you can go in the opposite direction. So if you have if the integral from t to b of f of x dx exists for every number t is less than or equal to b, then you can think about the integral from negative infinity to b of f of x dx, and you just say the limit as t approaches negative infinity of the integral from t to b f of x dx, if the limit exists. Okay, and these improper integrals are called convergent if the corresponding limit exists, and divergent if the limit does not exist. And these terms we're going to become really familiar with when we get to infinite sequences and series in chapter 11. You can think about the convergence or divergence of a series. And because of the similarity between the two, that you also think about improper integrals, at least the infinite ones, as convergent or divergent. Now, what about if you're integrating something like this from negative infinity to infinity? Well, to do this, what you do is you just pick a finite point in between, anywhere in between negative infinity and infinity, and you integrate from negative infinity to that point, and then from that point to infinity. And you just have two separate improper integrals that you add together. Okay, here they're just stating that just like a regular definite integral, you can interpret it as an area under a curve if the integral is always positive or always negative. But, even if it's not always positive or always negative, you can think about it as the net area. So, I mean, it's the exact same idea. Going off to infinity, it's the exact same idea as how you interpret a regular definite integral between two finite points, right? It's a net area. But if the function is always positive, then it's like the actual area under the curve, even going off to infinity or negative infinity. Okay, so here they do example problems, and these are pretty simple. It's really more about, well, they're not simple. They're simple if you know how to take limits and evaluate definite integrals, right? So like you're taking a definite integral with a variable as one of the limits of integration, and then you're taking the limit of the resulting function. So if you can take limits and do definite integrals, then the mechanics of working these type 1 improper integrals is not a big deal. So it's really the concept is what you want to wrap your head around. But we're still going to work a bunch of example problems. Now if we take a look at this example though, so this form comes up a lot. It's related. You'll see this kind of idea with series as well. So the integral from 1 to infinity of 1 over x to the p. So for what values of p is this convergent? So in the first example, the integral from 1 to infinity of 1 over x was evaluated, and that was divergent. So you know that this is going to be divergent for when p is equal to 1. So now they assume that p is not equal to 1 and evaluate this. So if p is a constant, then you take the limit as t approaches infinity from 1 to t of this. You do the integral. So x to the minus p plus 1 over minus p plus 1 taken from 1 to t. You get this function of t. Now take the limit as t goes to infinity. And analyzing this, you can see if p is greater than 1, then the integral actually converges to the value 1 over p minus 1, if p is greater than 1. If p is less than 1, then the limit goes to infinity, so the integral diverges. And I guess we're just assuming p was positive here. Well, yeah, because p has to be positive or else you're changing the integrand, right? If p is negative, then you're looking at a different problem. If p is negative, then you have x to the p, like if p is negative 2, then this is the integral of x squared. So yeah, it only makes sense to think about p being greater than 0. So yeah, if p is greater than 1, if we come here, if p is greater than 1, then this converges to 1 over 1 minus p. If it's less than or equal to 1, it diverges. This integral, the integral from 1 to infinity of 1 over x to the p dx, where p is greater than 0, it converges if p is greater than 1 and diverges if p is less than or equal to 1. And when it converges to 1 over p minus 1. Just keep this in mind. This is an important integral in form here in relation to series, but it's also good to keep this in mind in relation to improper integrals as well. Okay, so that was type 1 improper integrals. Now we're going to look at type 2. And mainly these are about how you can integrate across infinite discontinuities, but really these apply to any discontinuity. So suppose that f is a positive continuous function defined on a finite interval from a to b, not defined at b, but defined at a, but has a vertical asymptote at b. Let S be the unbounded region under the graph of f and above the x-axis between a and b. For type 1 integrals, the region extended indefinitely in a horizontal direction. Here, the region is indefinite in a vertical direction. The area of the part of S between a and... So, okay, yeah, we're defined at a, and we have a vertical asymptote at b, and we're trying to think about the definite integral, which is, the area under the curve between like a and b. And we're going to do a similar procedure. We're going to think about the definite integral from a to t, and then we're going to take the limit as t approaches b from the left of the integral from a to t of the function. That's the idea. And you could think about if you had the vertical asymptote on like the left boundary, then you would take, it would just be the opposite. It would be the limit as t approaches b from the right of the integral from t to b of the function. And so that's how type 2 integrals work. And so I'm going to make another video that's going to illustrate this clearly, but type 2 integrals apply for all discontinuities and all endpoints that if you're not defined at the endpoint. And you'll see I'm going to make another video that's going to illustrate what I'm talking about clearly. So the idea is if f is continuous on an interval, so it's it can't be undefined at both endpoints, then you have to like take a limit approaching both endpoints. You have to, if that's the case, then you have to separate it up into two different integrals. Watch the next video. I'll illustrate how that works. But so to do an improper integral, you have to be defined at one of the endpoints. And then you're dealing with another endpoint that's not defined because it's a discontinuity or it's an endpoint or whatever, right? And then what you're going to do is you're going to take the limit as t approaches the undefined endpoint or the discontinuity or whatever from the left or the right is what you're going to do. So, okay, here, let's say the endpoint is the right endpoint. Then you say that the integral of f of x dx from a to b is the limit as t approaches b from the left of the integral from a to t f of x dx, if the limit exists. If it's the other way, if the left endpoint is undefined, it's the discontinuity or whatever, then the integral from a to b of f of x dx is the limit as t approaches a from the right of the integral from t to b fx dx. The improper integral is called convergent if the corresponding limit exists and divergent if the limit does not exist. And yeah, they're really talking about here convergence and divergence in relation to the infinity, an infinite discontinuity. Convergence and divergence, you're thinking about infinity. And so this just gives the illustration of integrating across a discontinuity. So if f has a discontinuity at c, then the integral from a to b fx dx, if c is between a and b, is equal to the integral from a to c fx dx plus the integral from c to b fx dx. And again, so check out the next video. It's either the next video or maybe two from this one. I give a really good illustration of, it's called, the video is called The Power of Improper Integrals. And I give a really good illustration of how you operate with type 1 and type 2 improper integrals and what they all mean. Okay, so here they give more example problems. I think the mechanics of doing this is really simple. Again, if you can evaluate limits and if you can evaluate definite integrals, then the mechanics are easy. It's really but we're still going to work a bunch of examples, but it's really more of the concept of this that you want to grasp. I like what they illustrate here. What they show is that, so here's an improper, or no, here's just a definite integral, right? And if you find the antiderivative, which is, so 1 over x minus 1, that's the natural log of the absolute value of x minus 1, and you plug in the limits of integration. So yeah, like if we come here, here's the natural log of the absolute value of x minus 1, that's the antiderivative. Plug in the limits of integration. Natural log of 2 minus natural log of 1 is natural log of 2. So is this correct? Well, no, it's not. Why? Because you have to take a look at the function that you're integrating. So like this has a vertical asymptote at x is equal to 1. You can integrate across a vertical asymptote, but you have to do it with improper integrals. You can't just find the antiderivative and plug in the limits that way. You have to integrate it the correct way, taking the limit approaching the discontinuity and then like you have to separate it up. And that should be clear here because the natural log of the absolute value of x minus 1, natural logs don't have any vertical asymptotes. Well, no, they do at like the endpoints. Yeah, so when x is equal to 1, natural log of 0, that's like going to negative infinity. So you can't, you're not, that's how this this ends up giving you an answer because you're just plugging in natural x is equal to 3 and x is equal to 0. You're not plugging in x is equal to 1. But you should see that you're going across like the natural log of is 0, which that doesn't make sense, right? When you think about like areas under the curve, you can't do that. So this is wrong because the integral is improper. It must be calculated in terms of limits. Okay, a comparison test for improper integrals. Sometimes it is impossible to find the exact value of an improper integral, and yet it is important to know whether it is convergent or divergent. This is like the same idea with series. We're going to learn about series. Series are like this. Sometimes you can't find the value for a series, but you still want to analyze to see if it's convergent or divergent. In such cases, the following theorem is useful. Although we state it for type 1 integrals, a similar theorem is true for type 2 integrals. So the comparison theorem states that suppose f and g, functions f and g are continuous functions with f is always greater than or equal to g, which is always greater than or equal to 0 for all x is greater than or equal to a. Okay, so you can see that they illustrate that here. If the integral from a to infinity of the function f is convergent, then the integral from a to infinity of g must also be convergent. And that makes sense. I mean, it's not an official proof, but you can see why that would make sense. If f is convergent, like if the area under the curve of f going from a to infinity converges to something, then so would the area under the curve of a if it's always less than f, right? But then there's also another way of looking at it. If the integral of g from a to infinity is divergent, then that means that the integral from a to infinity of f is going to be divergent. So there's two ways of looking at this comparison theorem. But you can notice that there's also two inconclusive situations. If you found that the integral from a to infinity of f was divergent, then it wouldn't tell you anything about a. Maybe a is convergent, or maybe it's divergent. You don't know. Okay. But so this comparison theorem, it's like a parallel to this with series is the comparison test for series, and it's the exact same idea as this. So let's take a look at this example. They want to show that the integral from 0 to infinity of e to the minus x squared power is convergent. So we can't evaluate the integral directly because the antiderivative is of e to the minus x squared is not an elementary function. So we write, they separate this into two separate integrals, the integral from 0 to 1 of e to the minus x squared dx, plus the integral from 1 to infinity of e to the minus x squared dx. And observe that the first integral on the right-hand side is just an ordinary definite integral. In the second integral, we use the fact that for x is greater than or equal to 1, we have x squared is greater than or equal to x. So minus x squared is less than or equal to minus x, and therefore e to the minus x squared is less than or equal to e to the minus x. And so since e to the minus x you can integrate, so this is e to the minus x. And so since e to the minus x you can integrate and show that it's convergent, and then e to the minus x squared going from 1 to infinity is always less than e to the minus x, then you've proved that the e to the minus x squared is convergent by the comparison theorem. And this is an important idea to illustrate that all that matters, you might say, well, what number are you allowed to start at to do this theorem? It doesn't matter. Like every single function, like the integral of any function from 0 to any number, any finite number, as long as it's like a continuous function, there's no like discontinuities or anything that like make the integral not exist or something. But like there's a finite area under a curve. If you going from 0 to like a billion, 0 to 1 billion, there's an area under the curve. It's convergent. It's all about the infinity portion. So if you can start at any number, and it doesn't matter where you start. If you can prove that going from that number off to infinity that the integral is convergent, then the entire integral is going to be convergent. It's all about the infinity portion. Okay, so we just showed that the integral from 0 to infinity of e to the minus x squared dx is convergent without computing its value. In exercise 72, we indicate how to show that its value is approximately 0.8862. And you can see they plug in some t's here. And as t increases, it looks to be approaching something, because that's the idea. As t goes to infinity, the fact that it's convergent means the integral equals something. It equals a number. That's what the fact that it's convergent, that's what it means. And so t is equal to 1, 2, 3, 4. As you plugged in t is equal to a million, a billion, you're going to be really close to what it's actually converging to. And you can think about that's how you could approximate it, is you could plug in like t is equal to 50, you know. In probability theory, it is important to know the exact value of this improper integral, as we will see in section 8.5. Using the methods of multivariable calculus, it can be shown that the exact value is square root of pi over 2. Table 1 illustrates the definition of an improper integral by showing how the computer-generated values of the integral from 0 to t e to the minus x squared dx. So this is computer-generated. They're approaching square root of pi over 2 as t becomes large. In fact, these values converge quite quickly because e to the minus x squared approaches 0 very rapidly as x approaches infinity. Okay, let's look at this last example. The integral from 1 to infinity of 1 plus e to the minus x over x dx is divergent by the comparison theorem, because you can just take we know the 1 over x, if you put that into an improper integral from 1 to infinity, this is divergent. And you can see that. So e to the minus x, like e to any power, is always positive. Even e to the minus x, this is just going to be less than 1. So if e to the minus x is always positive, no matter what, then 1 over x, that means this numerator is always bigger than this numerator. So that means this is always less than this, but this is divergent. So by that kind of the other way of looking at the comparison theorem, this integral must be divergent. Okay, so now let's work some example problems.